and it will get saved.
नव्हतो खेळत. होय.
Okay, so good morning, everyone. So everyone can hear me, right?
Yes, sir.
Okay, so before starting the lecture, so I just wanted to ask regarding the alternative options for lecture, Tuesday's lecture and the Wednesday's tutorial. So I sent all of you an email regarding that. So if you are fine with both the options, then it's fine. You do not need to reply. But if any one of you does have any problem regarding any one of those two alternatives, then please send me an email. Okay. by 6 p.m. today. So if I do not get any email from you guys, then I will consider those two alternatives from tomorrow. Okay. So let's start from the end of the last class. So what was the aim in statistical inference? Its aim is to infer about P, or specifically P composed X inverse based on sample X. Okay, so this is the aim. So this is the model. P is the model, and this X characterizes the feature. So that the feature we are interested in. So that means we are actually interested in P composed X inverse, which is simply the log or the distribution of X. Okay. So this P is somehow giving you the or quantifying the uncertainty that is involved in the sample in the sampling, and this X is characterizing the feature that we are interested in. So overall, we are the aim is to infer about this distribution based on the sample X. Okay. So so regarding the model, so model generally is of two types. One is a parametric model. So here you already know, I think. So if you can write this P as P theta, where theta belongs to some space which is a subset of the d-dimensional Euclidean space, where D is some natural number. Okay. Then the model P is parametric. So you need some parameter. This theta is a parameter. Okay. So any question? Okay.
Sir,
So
what does it mean when, what does it mean when P is similar to P theta? How is it defined?
Similar means P is same as P theta, where theta is characterizing the probability measure P. That's it. So for example, you can consider, let me write it here. So for example, this P theta may be normal with mean theta, variance 1. So here, this theta characterizes the normal distribution, right? So for example,
Yes.
So you may be interested only in this class of model. So here, this theta characterizing the whole family of the model, right? So here,
Yes.
this theta is the parameter, and this model is a parametric model. Why? Because the number of parameters that you are considering, that should be finite, first of all. That's why the D belongs to natural number, and yeah, and that is a requirement for a parametric model. For parametric model, so the parameter space should be a subset of some Euclidean space. Okay, and that that dimension should be finite. It cannot be R infinite. Okay.
Yes.
And if this is not true, then it's non-parametric. So when P is not parametric, so that means there may be two choices actually, two possibilities actually. So one is that there is no theta or no parameter, and the second one, no parameter, I should write, which characterizes the underlying family. The second possibility is that this theta belongs to some parameter space, which is actually a subset of R infinity. Okay. So this is simply the sequence space, and if theta is subset of that sequence space, then actually the model is non-parametric. And if there is no parameter, then it's non-parametric, obviously. So examples. So first one is that this normal theta belongs to R. Okay. So this is this family. So sometimes this whole thing is called a model. The whole thing, that means normal theta1 theta belongs to R. This is the model. Or sometimes it is called a family of model. It's simply the nomenclature, nothing else. Okay, so this is parametric. Second one, say binomial NP. So it's parametric because there is only one parameter P. Third one, all distributions symmetric around 0. Fourth, it's distributions or continuous distributions which have expectation of x to the power of 4 finite. Okay, that means the fourth moment is finite. So in the first two examples, so this family or this family, these two families are characterized by the underlying parameters. Here the parameter is theta, and the parameter is p, and these are the parameter spaces. This is R is the parameter space here, and the parameter space in this case is simply the open interval 0, 1. But in the examples 3 and 4, so there is no parameter involved. So you are looking into all possible distributions, all possible univariate distributions, which is symmetric around 0, right? So there is no parameter involved here. Here, the distributions you are looking into that have fourth moment finite. So you can think of all possible continuous distributions which have fourth moment finite. So there are infinitely many choices. Even if you think of this fourth moment to be a parameter state, so in that case, so actually you cannot think this as a parameter because that is not characterizing the distribution, right? Because there may be other things that may, if the distribution may change with that thing. So that's why here also there is no parameter, you can say. And since there is no parameter involved in 3 and 4, these are non-parametric models. And obviously, whenever you want to infer about the underlying family or underlying model, it is obviously easier to infer about the parametric model. Because in this case, if you simply infer about theta or infer about p, then actually you are done. But in this case, it's very difficult, much more difficult than the parametric one, because you are looking into much bigger family of models here in these two cases. So that's why the parametric inference is kind of more precise than the non-parametric inference, because you have more information here. In parametric inference, actually you have the distributional information here. Here it's normal, here binomial, something like that. You always have. But in non-parametric case, you actually do not have that. You only have some kind of symmetry or some existence of moments, something like that. Or the underlying parameter space is infinite dimensional. So in these cases, since you are looking into much bigger class, so that's why the inference is not so precise. But obviously, since you are looking into much bigger class, the procedure of inference that is more that is that you can more that is more applicable, I can say, because you are looking into much bigger class. Okay, so there is kind of trade-off. In parametric, the inference is more precise, but it's very restricted, the inference procedure, because you are looking into much smaller class of families. But in non-parametric, the inference is not that precise, but actually since you are looking into much bigger class, the inference procedure is much more applicable. That's kind of the trade-off. Okay. So in this course, you will, in most of the situations, you will look into the parametric model, in at least in the first half of the course. In the second half, when you will see the asymptotic things, then maybe you will come across some non-parametric methods. Okay. Okay. So one more thing is that note. So we have this thing, right? From here, we are going to, let's say, from now on, since we generally consider the sample size of size n, so let's write this as x card, which is of size n, and let's call this Rn, Prn, and measure P composed x. So our aim is to infer about this distribution based on the observations that we obtained on x card, right? Okay, so so clearly, actually, the script f, which is the sigma algebra on omega, the sigma algebra on omega contains all information about omega. However, we are looking into script f through x card. That is, we are only looking into sigma of x card, which is simply the sigma algebra So this sigma of x card is nothing but the sigma algebra generated by this kind of sets. Okay, so you have already seen that to define to get some random variable or random vector, you need that function, the inverse of any set with respect to that function belongs to script f, right? So you already know that this sigma algebra is a subset of script f. So is this fine, this statement? So first of all, this x card is a random vector. So that's why you already have the restriction that this type of sets belong to script f. There is a restriction due to the definition of random vector, right? Now I am saying that since this type of sets belong to script f and script f is the sigma algebra, so that means since so this whole thing is nothing but the smallest sigma algebra generated by this type of sets. And this is a sigma algebra, so that means the smallest sigma algebra should be contained in the bigger sigma algebra. So that means we are simply looking into this smaller sigma algebra rather than looking into script f, right? So although this scriptf contains all the information, actually we are looking into a chunk of scriptf, not the whole scriptf. So we need the assumption. So hence we need the assumption that this sigma algebra, sigma of x card, contains all the information. Because we are simply looking into this sigma algebra, we are not looking outside. So that means we need this assumption. And actually this is valid, right? Because whenever you are looking, you are interested in height, then actually you do not need the information about weight on the population omega, right? You only want to know about the height. So that means the random vector that characterizes height, the information that you obtain based on that is enough actually. So that's why this assumption is valid. Or at least we have to assume this, otherwise we cannot make inference. Okay, so is this clear? If not, I can explain again. Okay, I believe it's clear. So the assumption is that the sigma of x curve, which is the sigma algebra generated by x curve, that contains all the information that we want actually. Okay, so now given an observed sample of x curve, what should be the first step? So now you are given suppose an observed sample of the random vector x curve. Then now the question is, what should be the first step? So first step, what we generally do. So first of all, for example, say whenever we are interested about average height of a population, we generally look into the average of this sample, right? We generally consider the method of movement kind of thing, right? Whenever we are interested about the average, then we look into the average of the sample. Whenever we are interested about, say, about the variance, then we look into the sample variance. We generally do this kind of things. And why we do that? We do that because if the sample variance or the average contains all the information instead of this sample, then actually we are somehow getting much simpler statistic, right? Statistic of the estimator. Instead of looking into the whole sample, we can simply look into a single function of the sample, and that will somehow giving you all the information. So that means the first step is to find a function of this x1 to xn, or more precisely it's called xn, which contains all the information. So if you consider the function t of x curve, and you want to somehow find this t such that to find this t such that the sigma algebra generated by this T contains all the information. So if you can find a single function or maybe 2 or 3 functions of the sample, and if you can claim that the sigma algebra generated by that function contains all the information, you somehow making the problem simpler, right? You are not looking into n things, you are looking into 1, 2 or 3 or some number of things, right? Some number of functions of the sample.
Excuse me, sir.
Yeah.
Excuse me, sir. Sir, what do you mean by the sigma algebra generated by a function? Do you mean the range or image of the function?
No. So this T is again a random variable, right? Random variable,
Yes.
random vector,
Yes.
right?
Yes. Okay,
Yeah,
so
so
T inverse of Borel sets, basically.
yeah,
Do you mean T inverse
definitely.
of
Yeah,
Borel
so
sets?
if this T is say has only one component, then you are simply looking into the T inverse of Borel sets of real life. That's it.
Yeah. And if it is
So
multivariable, then Borel sets of some R2, R3.
RD, yeah, RD for some D more than equal to 1.
Okay. Thank you.
So in general, this sigma of T is a subset of sigma of X curve. Hence, finding sigma of T or sigma of T will further reduce the problem of inference. So first of all, we had this descriptive, which is the original sigma algebra. Okay, so then from that original sigma algebra, we came to this sigma of X squared, where X squared is the sample, and from here we are somehow trying to find some function of this X squared such that even this sigma algebra can be made more simpler. Okay. Okay, so this T, so this type of T is what is called the sufficient statistic. So first of all, what is a statistic? So statistic or an estimator is nothing but the function of the sample only. So it does not involve any parameter. So a statistic or an estimator is a function of the sample. It does not depend on the parameter. Does not depend means functional. Or I should write it clearly. So a statistic or an estimator is simply a function of the sample only. It is not a function of the underlying parameter or underlying model. So in case of parametric models, you can talk about parameters. So that's why when writing the definition, I can write that it is not a function of the parameter. But whenever the model is non-parametric, then you should write that it is not a function of the underlying model. You cannot say parameter. Okay. So this T, so somehow trying to reduce the complexity of this sigma X squared and finding this T, this is called the procedure of sufficiency. So what is the aim? So first step is to find a sufficient statistic T, that is to find that sigma T contains all the information about the model. Obviously, we are inferring about the model. Okay, that is what sufficiency is. So in other words, what you can say? In other words, you can say that given the information sigma T, there is no other information available in sigma of X card about about the model. Okay, right? It's in other words, you can say this: whenever you have the information about this sigma T, you do not actually need this sigma X curl anymore. It's enough to have this sigma T, right? Or it is enough to have, you have to know this T. Okay. So that means this is the definition of sufficiency. This says that given the family of models T is sufficient if the conditional distribution of X card given T does not depend on P belongs to P or on any. Okay. So that means even if you change the underlying model, that means just think about normal theta 1. Even if you change the theta, the conditional distribution of the sample given the statistic, the sufficient statistic, will not change if you change theta. It's kind of similar. So the specialized case for the parametric family simply tells you that for this P, this X card given T should not depend on theta. That is what sufficiency is, right? So clear, right? Okay.
So
Yeah.
could you
Yeah.
just explain that third statement? Conditional distribution does not depend on any P.
Okay. So you understood the second one, right?
Yeah.
The second one tells you that if you already know sigma of T, let me write it again. So the second one is simply tells you that if you know sigma of T, then sigma of X card is not required anymore. It's kind of the second and first one together. So that means whenever this you know about this sigma t, then actually you do not need sigma of x squared. That means if you know this t, you can throw this x squared. So that means this sigma t contains all information. So it's kind of similar in probabilistic term by looking into the conditional distribution. So what is the conditional distribution? Is in conditional distribution, what you say that x squared given t, that means you already know this t, right? After knowing t, you are looking into what else you have in x squared. That is the conditional distribution. And that actually the distribution of x squared given t does not change with t. Or I should write this probability of x squared given t does not change with t belonging to p. So similarly, if it is a parametric family, you will write like this: does not change with theta belongs to script. Right?
Yes, sir. Fine.
Clear, right?
Yes, sir.
Okay. So the conditional distribution is nothing but you are looking into given something, given the information, what else you have in x squared left. So now when this information is enough, you actually you do not have any more information in this distribution of x squared, and that's why about the model, obviously about the model. So this probability, this conditional probability, will not change with the choice of p. That is the definition of sufficiency. And whenever it's a parametric, it does not depend on the parameter t. That's it. Okay. So the main point about sufficiency is that yeah. So first of all, you had that script f which contains all the information about the population omega. Now from that you came to sigma of x squared. Sigma of x squared is simply the sigma algebra generated by the sample x squared, and you assume that the x squared, that sigma algebra contains all the information that what you actually need. And then from there, in sufficiency, you want to find a function t of x squared such that sigma t contains actually all the information. Then you do not need sigma of x squared anymore. You can simply throw x squared and retain t. Okay. So that is what sufficiency is. So let's look into an example, few examples. First one. So mathematically, you know how to find the conditional distribution. That is fine. But what is the intuition actually? So let this x1, x10, these are all from Bernoulli. Okay, these are all IID. So IID means these are, so x1, xi, and xj, they have the same distribution, that they have the identical distribution, and they are independent. Independence is defined with respect to the sets, let you know. And so I should write it actually. What is the definition of independence? So two sets, A and B, are independent if probability of A intersection B is probability of A into probability of B. So this is the definition of independence, right? So now to random variables, x1 and x2 are independent if probability of x1 inverse of A intersection x2 inverse of B, that is simply probability of x1 inverse of A, probability of x2 inverse of B, for all A, B belonging to the model signal. So what is this probability? This probability is simply the probability of the joint, right? So this is nothing but probability of x1 lying in A and x2 lying in B. This probability is same as this, and again this is nothing but probability of x1 lying in A multiplied by probability of x2 lying in B. So if you think about these inverses, it is easier to understand what is the definition of independence. So because the independence is defined with respect to state first, and after using this definition, you are actually defining the independence of two random variables or more than two random variables. Okay. So here these are IID means. So first of all, this thing is true not only for any two, for any collection of random variables from this set, and moreover, this xi, and if you consider xi and xj from here, they have the same distribution. So that is what IID is, right? Okay, actually you guys already know this thing, I believe. Okay, so now there is Bernoulli P. So you can simply look into the tossing a coin, right? Tossing a coin with probability of head being P, right? So now think of n independent trials of tossing a coin with probability of head equal to P. Okay, so in that case, so if you want to infer about this P, so that means to what is P? P is simply, you can say, you know the what is called you know the three definitions of probability, right? One is the classical one, second one is the relative, or I think that is the asymptotic one, and the third one is the measure theoretic one. So the second, if you recall the second one, what is the second one? Second one is nothing but P is approximately equal to the proportion of heads, right? In a long run of independent trials, right? That is what P is actually. That is the definition of probability with respect to the that relative frequency approach. What you call actually, that is, I think so. Okay, so P is nothing but the proportion of heads. So that means whenever you want to find the proportion of heads, what is important? So hence, to infer about P, what is the important thing? What is the only important thing? To find the proportion of heads?
The frequency.
Yeah, frequency. That means only what is the important thing? Important thing is simply the number of heads, the total number of heads, right? The total number of heads is enough actually. Why? Because if you know the total number of heads, you already know the number of independent tosses that you have. You can simply divide this total number of heads by that number, then you will get the approximate value of P, right? So that how you generally infer. And hence, so my point is that to infer about P, the number of heads is important. The position of head and tail, those things are not important, right? So if I say this, actually this head tail head PP and head PPPH, these two things are same, right? In this case, because here the number of heads is 2, number of heads is 2. The position of head, that really does not matter, right? So what is the number of head? Total number of head. Total number of head is nothing but the sum of xi. So that's why the sum of xi is sufficient here. So you do not actually need the positions. So after having the information about the number of heads, what is the information that is left in this sample? The information that is left in the sample is simply the position of heads, right? Nothing else. But if you look into this definition of the probability, then actually to infer about P, so it is very easy to understand that the number of heads is enough to infer about P. So that means the position of heads, that is not important, not at all important. So that means you can simply throw the position of heads and you have to retain the total number of heads. So clear? So you can always do the math, actually find the conditional distribution of x curl given the sum that you can find actually, and you will see that that conditional distribution is that probability that this xi is equal to xi for all I, given the sum of xi is t, that is equal to, that is I think the two things below. If p is not equal to sum of xi, and if p is equal to sum of xi, this is simply 1 by NCE. So that means here the conditional distribution does not depend on p. That means does not depend on the model. So this is the math, but the underlying what is the underlying reason or the intuition? The intuition is that whenever you want to find the proportion or you want to infer about the proportion, then actually you need the total number of heads. You do not need the position of heads, right? So that's why it is enough to look into the sum of xi instead of looking into the sample. Okay, clear? I think it's clear, right? Okay. So this is check this. Second one. So I should write the space the parameters. So here sum of xi is again is sufficient. Also check this using the definition. Third one. Suppose you have only one observation, that is from Cauchy. Let's say 0 sigma square. This is simply the scale, nothing else. Then what is the sufficient statistic? Suppose you have only one observation.
Median. The median.
Yeah, median you can say. Median means here there is only one observation. So this is the median.
The observation itself
Observation itself is always sufficient, right? The sample itself is always sufficient. So what is a non-trivial choice of sufficient size? So think about, so just forget this Cauchy. Think about normal 0 sigma square. Okay. So in that case, you know that what is the sample variance. So sample variance, then also you assume that the sample mean is 0. Or sorry, it cannot be possible because there is only one observation. But what is the sample variance in that case? The sample variance in that case is 0, obviously, because there is only one observation. But my point is that here the distribution is symmetric, right? So since this is symmetric, if you want to say something about the scale, then you actually do not need the sign of x. You only need the absolute value of x, right? Only need that. So then this absolute value of x is sufficient. Right? Because whenever you find whenever you want to infer about sigma square, then actually the sign is not important. And if you find the probability, like probability of x equal to or should write it like this, is here that x given absolute value of x is equal to say y, that is equal to y with probability half and minus y with probability half, right? So whenever the absolute value is y, the possible choices of x is either y or minus y, nothing else. And the probabilities are half because this is symmetric around 0. Okay. The third one is a non-parametric example.
Sir, excuse me, sir.
Yeah.
Sir, when you write mod x, do you mean the mod of the expression 1 by 1 plus x square or something like that?
No.
Like,
Absolute,
what do you
the absolute
exactly
value of
mean?
x.
Absolute value of x, okay, and x will return a real number, right?
Yeah, so x
like,
is Cauchy 0 sigma square, so x is a real number, but it's random.
So, yeah, okay, I got it. Yes, thanks.
Yeah, the definition of absolute value, right? You know that.
Yes.
Fourth one is I should say something. Okay. So this is the model. In this case, here you are looking into the collection of all absolutely continuous distribution. So what is the absolute continuous distribution or absolute continuity? So given space G. So this is a general space. Okay, do not think this as omega scripted. This is some other space, some general space. Measures mu and mu. Mu is absolutely continuous. with respect to nu, or the notation is this. If mu of A is 0, we imply that mu of A is also 0. So what is the definition of measure? I think you already know what is the definition of measure, but let me briefly go over the definition. So mu is a measure on omega script g if first one is that mu is a function from script g to r plus, which is close 0 open infinity. Second one is mu of the null set is 0, and the third one is that if, so it's similar to the probability, if these sets are disjoint and belongs to script G, then mu of union of an is simply the sum of mu of an. This is the definition of a measure. Okay. So in case of a probability measure, the value that measure can take is between 0 and 1, right? That is the only difference. The rest are the same. Okay, the first one is simply mu is a function from the sigma algebra to the non-negative real line. Second one is that the measure of the null set is 0, and the third one is that the measure mu is actually you can say countably additive. So that means if you have a sequence of disjoint sets belonging to script G, then mu of union of n is simply sum of mu of n. The important thing is that the sets should be disjoint. Okay. So this is the definition of measure. Now I am saying that the absolute continuity is between two measures and not between. Actually, absolute continuity is of a measure with respect to another measure. So here this mu is absolutely continuous with respect to mu. So this is important. The absolute continuity is directional. So that means mu is absolutely continuous with respect to mu. If this is true, then it may not be true that this mu is absolutely continuous with respect to mu. Okay, that may not be true. So that's why this is important. You should write always that mu is absolutely continuous with respect to some measure mu. And the notation is this, and the definition is that if mu of some set is 0, then mu of that set should be equal to 0. This is the definition of absolute continuity. So we need this first. So in general, the absolute continuity in RDR, or I should write it more generally. If you look into any d-dimensional Euclidean space and the Borel sigma algebra on the d-dimensional Euclidean space, and that absolute continuity is generally defined with respect to the Lebesgue measure. So these things are important. Why? Because in most of the situations, in many situations in inference, we generally look into the PDF or PMF, right? We generally we do not look into the CDF. We go to PMF or PDF, which is simply the derivative of the CDF. So since we look into those, so those things only are defined whenever the underlying model or underlying measure is absolutely continuous with respect to some other measure. In case of PDF, it's the Lebesgue measure. In case of PMF, it's the counting measure. There is another measure that is called counting measure. Okay, so in general, the absolute continuity in on RD or specifically on R is defined with respect to the Lebesgue measure. So clear, right? The definition of measure, then the definition of absolute continuity. So one quick example is that any normal mu sigma square is absolutely continuous with respect to the Lebesgue measure. And what is the Lebesgue measure? This Lebesgue measure is nothing but Lebesgue measure is generally denoted by lambda. Lambda of some set A is simply the length or area or volume of A. Okay. So, for example, if you consider an imaginary coordinate system here and consider this board as the two-dimensional Euclidean plane, in that case, the Lebesgue measure of this board, the surface of the board, is simply the area of this board, nothing else. And if you think of this board as a 3D object, obviously this is a 3D object. In that case, the Lebesgue measure of this board is simply the volume of the board. Okay. So in R, it's simply the length. In R2, it's the area. In R3 and above, it's simply the volume or hypervolume. That's it. Nothing else. Okay. So normal distribution is absolutely continuous with respect to Lebesgue. Similarly, the exponential. So all the continuous distributions that you have seen before, they are actually all the continuous distributions that you have seen before. Those are actually absolutely continuous with respect to the Lebesgue measure. Okay, and those are actually absolutely continuous. Those are not only continuous; those are absolutely continuous. There is a difference between absolute continuity and continuity, but I'm not going to go there. But yeah. So the point is that whenever you say that some distribution is absolutely continuous on RD, BRD, so generally it is meant that absolute continuity is with respect to the Lebesgue measure. Okay. So then there is another important measure other than the Lebesgue measure. So there are three fundamental measures in general in measure theory. One is this Lebesgue measure. Another one is the probability measure that you already see. Or any sort of probability is a probability measure, and the other one is the counting measure. This counting measure is simply counts. So if gamma is a counting measure, gamma of some set A is simply the cardinality of it. Cardinality of it. That's it. So you simply count the number of objects that is inside the set A. That is the counting measure of that set. Okay. So so whenever you are saying absolutely continuity on RD, BRD, then it is a Lebesgue measure. But this binomial in P or the Poisson, these are all absolutely continuous with respect to gamma over this space. Okay. So instead of looking into this space, if you look into only the set of natural numbers union 0 and the power set over that, the power set is always a sigma algebra. So then if you consider this space, then over this space, these distributions stand, and these distributions are absolutely continuous with respect to gamma, right? Gamma is the counting measure. Because if gamma of some set is 0, then the probability under this distributions of that set is 0. So similarly here also. Okay. So, for example, what are the general sets that have normal measure 0? So, for example, if you consider any finite number sets, for example, let's consider 1, 2, 3, 4. That set has normal measure 0, right? Because the Lebesgue measure of that set is 0. Because there is no length inside that set, right? The length of that set is 0. So that's why you can, whenever you think of absolute continuity, you should think with respect to the Lebesgue. It is easier to think because Lebesgue is nothing but length, area, volume, something like that. Okay, so I deviated a lot from the example actually, but it's important. This thing. So actually, the important thing is that whenever you are looking to some family which is absolutely continuous with respect to Lebesgue measure, then actually it is enough to look into the PDF of the PDF involved in that family, right? Nothing else, because then those PDFs will characterize the family. So my point is that note when P is the family of models, and P is absolutely continuous with respect to some other measure. Let's call that measure. Let's call that measure kappa. Family of models, and yeah, for all P belongs to P, then enough to look into the PDF, right? What is the PDF? PDF, whenever PDF exists, is the derivative of the CDF, right? So you can think of this. So this dp of d kappa is the this is the definition. I don't know the derivative of p with respect to kappa. And there is a theorem that says if mu is absolutely continuous with respect to nu, and nu is sigma finite, then d mu by d nu exists. So what is sigma finiteness? Sigma finiteness means there exists a sequence an of sets belonging to the underlying sigma algebra such that mu of an is finite for all n, and union of n is omega. So this is a theorem which tells that whenever some measure is absolutely continuous with respect to the another measure, and this measure is sigma finite, then actually this derivative exists. And whenever this derivative exists, this derivative is nothing but the density. This is a random Nikodym derivative. Whenever this derivative exists, you can actually characterize this family script P as the family of these densities or family of these derivatives, right? You can go to the density from CDF whenever this density exists, and this theorem tells you when the density exists. Okay, any question regarding? I said many things about the measure. I'll actually write all these results in somewhere. I'll upload as a supplementary note. Okay. Because I'll need this, the existence of this derivative in the next theorem. What is the next theorem? Insufficiency. What is the next theorem? You guys all know the theorem.
NP lemma.
The NP lemma is in testing, right? It is the Neyman-Fisher factorization theorem.
Continuity, consistency.
Neyman-Fisher factorization theorem, right?
Yes, sir, factorization theorem.
Yes,
Yeah,
sir.
so in Neyman-Fisher factorization theorem, you generally look into the density. You write the density of X curve in terms of few things. So that's why this derivative is important. It's needed. So one last thing that I want to say is that I'll do the example in the next day. Maybe tomorrow I'll do that. But today I just want to say is that normal 0, 1 is absolutely continuous with respect to the Lebesgue measure on R, VR, and lambda is sigma finite. Why? What is the definition of sigma finiteness? You need to find a sequence of sets such that the individual sets have finite measure, and the union of those sets is simply the whole space. Why? Since lambda of minus n to n, that is 2n, that is finite, is set. And union of minus n to n is simply R. And this minus n to n, these sets are open sets. So that's why these sets are Borel sets. Okay, so that's why this lambda is sigma finite, because you can simply consider this type of sets which are Borel sets, and individually they have finite measure. That's why lambda is sigma finite. And since normal 0, 1 is absolutely continuous with respect to lambda, it can be shown. So that means the derivative exists. The derivative of normal 0, 1 with respect to lambda at x, that you already know. What is that? It's simply 1 by root 2 pi e to the power of minus x squared by 2, right? This is the density. So in elementary class, you have seen this derivative with respect to x, right? The derivative of the CDF of normal with respect to dx, right? Here you are looking into d lambda. So these two things are same in this case, at least. So there you are looking into the derivative, which is nothing but some types of some form of Riemann integration, and here you are looking into the Levin integration. There is something different. Okay, so so today I covered few things from the measure theory, because these things are needed in future understanding of many results actually. That's why these things are needed. And I will do the example that I mentioned regarding the absolute continuous distribution tomorrow. Okay. And also I will also upload these definitions, all these things. I'll write somewhere and I'll upload them as a supplementary note. But that will not be enough, I think, for you guys to learn something about the measure theory. It is always better to look into some book. So I'll recommend you to look into the chapter 1 of Jun Shao's book. Okay, and only the parts of measure, and so whatever you have seen here, you can simply search in chapter 1, and you will find many things actually in that chapter. So I recommend you guys to look into that chapter 1 of Jun Shao. Okay, so any question? Okay, so I believe that's it for today. And one more thing is that please reply to my email if you have any problem regarding the alternative options, any of the alternative options. If you do not have any problem, then you do not need to reply. I'll wait until 6 p.m. today. If I do not get any reply from any one of you, then I will shift to the alternative options. Okay, for Tuesday and Wednesday. Okay, so that's it for today. Thanks. Bye.
Thank you, sir.